Okay, the last thing we're going to talk about for the school year is the life cycle of stars. This will end our conversation on outer space, and the last thing that we'll go over before the final. So, very similar to the way we've seen our solar system form, we're going to see other stars are going to form in a similar way. So we're going to see a lot of parallels or similarities with the formation of stars. So they're going to come from a nebula cloud of gas and dust, composed mostly of hydrogen with a little bit of helium. Within that nebula there's going to be varying regions when gravity causes this dust and gas to clump together. As these clumps gather more atoms or mass, they're going to start to pull themselves together into clumps, disks, accreting and condensing. A little bit of contracting as gravity is going to pull those gas and dust towards a core. And in that core we're going to start to see as gases get compressed, we're going to see temperatures increase, and the number of those collisions are going to increase when temperature increases. Density in the cores, as more atoms try to share the space, is going to increase. Just remember that again, temperature is a measure of the energetic movement of particles. We have here some examples of nebula clouds. Gas and pressure is going to increase as atomic collisions and density are going to increase in the core. And then we're going to get to what we call a protostar. This is as on their way to becoming a star, we're going to get to kind of like a disk forming where things are going to kind of get pulled into a gravitational, elongated, flat pattern, if you will. When gravity and pressure are going to start to get into what we call a hydrostatic equilibrium, essentially they're going to balance each other out. Accretion is going to stop, and at that time, if fusion takes over in the core, we have the birth of a star. And that's what we consider the formation of a star. So we start off with a nebula, gets into a disk shape or a little protostar, and then once fusion begins, then we have the star turning on or the sun turning on, depending on what we're looking at, whether it's our solar system or another star. We see here we have the protostar, very, very hot center as these gases are starting to take shape and get either pulled in, or they could even possibly then become planets if they don't get pulled into the sun in the center. As a star gets to a really hot ball of gas, it's going to spend the majority of its life fusing hydrogen into helium. And it's going to take place in their core, and that's going to allow them to emit light and heat and energy. The stars are going to spend the majority of their lives fusing hydrogen into helium. And then when that fuel source is gone, when the hydrogen is kind of used up and all fused, then there's going to be helium there, and some of the stars can start making helium into heavier elements like carbon. The more massive stars, which are more interesting, even though they are very, very rare, can start fusing carbon into even heavier elements, and that's where a lot of our heavy elements in the universe are going to come from. Also, when we get things like supernova explosions, that's going to help create a lot of those heavy elements. Throughout this whole process, that's the battle between gravity and gas pressure. We talked about equilibrium there. And it's crucial to keep this in mind as we talk about the life and death of stars. It's essentially this battle between gravity and gas pressure. For the most part, as we get towards the end of a star's life, hydrogen in the core is going to be gone. And at this point, we're going to start to look at the death of a star. If the star wants to maintain equilibrium between gravity and gas pressure, it needs to increase the temperature so it can then start to fuse together heavier elements. So the star is going to be forced to burn helium in an effort to maintain stability. Gravity is going to cause its core to shrink down a little bit, and that will increase the temperatures. And that's what's going to lead to it burning or fusing helium. To remain stable, the star is going to want to balance those pressures out. And gravity is going to cause the core to contract. Helium starts to burn inside the core, and that's what's going to cause it to then expand and become what we call a red giant as it starts to then burn that helium. And that's going to be essentially the first step after it starts to get out of its main cycle, or the main part of its life. It's going to go into a red giant, and that's when it starts to burn helium. It doesn't matter the size of the star, but at some point it's going to run out of fuel, no matter how big the star is. I mean, bigger stars are obviously going to change the amount of time it takes to go through this, and smaller stars aren't going to go through the same process as big stars, but eventually, no matter what it is, every star is only a finite amount of material, and it eventually is going to fuse or burn through that material. So gravity is going to take over. With this in mind, we're looking at the death of stars in three categories. We look at low mass stars, medium mass stars, and then the most massive stars. With the low mass stars and medium mass stars, they're going to go a lot of the times the planetary nebula route, and this is the kind of fate of our sun. It's going to eventually go to the planetary nebula route and become a white dwarf. When it does that, it's going to lose a lot of its outer shell, and it's going to be left with a core, very, very dense core, but about something the size of the Earth, and almost like a smoldering campfire, or ashes at the end of a campfire. It's just going to kind of glow, emit light, but eventually it's going to go completely dark, and from a white dwarf into a black dwarf, and not give off any light or heat over the course of time. But eventually, almost like I said, ashes at a campfire at the end. It's just going to kind of smolder out. Higher mass stars can get to what we call neutron stars. And with those, we could also get supernovas that can take place when a neutron star is created. The size of the neutron stars is often the size of a large city. It's kind of interesting that larger stars will end up dying and becoming smaller, and a lot of that has to do with the amount of mass that they have. If they have more mass, the stronger gravity that can compress them down into a smaller state, and allows them to go through these sometimes more interesting processes of larger stars. When the stars are extremely, extremely massive, they can generate giant explosions called supernovas. That's when the other layer of the stars are going to blast off into space, and that's what's going to essentially then lead to nebulas and the creation of new stars in a lot of cases. Once we start to get carbon burning inside the cores, when the helium of the core is gone, the core needs to maintain its temperature, and again the temperature is going to have to increase so it could then go from fusing helium into fusing carbon, and even fusing in some cases even bigger, heavier elements. Otherwise the gravity is going to take over, and it won't be able to do that. So we have here an example of a supernova explosion. The highest mass stars, they shrink to essentially a single point, and on the way to total collapse, they have this momentary neutron star and kind of a little a rebounding or a shockwave given off. But gravity ultimately is going to win, and nothing holds up, and they form a black hole. And not even light can escape a black hole. We do have different particles that do get out of black holes, a little bit of radiation that's given off, or a little bit of heat that's generated from these black holes, where we talked about Hawking radiation. Skip through that. With Hawking radiation, sorry about that little runaway there. With the Hawking radiation, eventually, over time, according to Hawking, that black holes are going to evaporate, or not grow, and they'll eventually shrivel up and shrink. Now, a little debate on how long that'll take, but over enough time, eventually black holes will even die off. Almost like, think of them as recycling systems of the universe, where they're going to take old stars and old galaxies and almost essentially then create materials that can then lead to new stars and new star systems and galaxies. So almost like a recycling plant. With talking about galaxies, there are different types of galaxies. Galaxies are a large system of stars, interstellar material typically containing several million stars, sometimes trillions of stars. And the mass between them, sometimes they are stretched out over hundreds of thousands of light years across. And there's usually large distances between them. There's two main types of galaxies out there. There's elliptical galaxies, essentially like a ball or a sphere shaped. Normally elliptical galaxies contain very little or no interstellar matter and consist of very old stars. They appear luminous bulges of spirals without the disk, so similar to a spiral galaxy, but they don't have the arms coming off in a lot of cases. At the centers of a lot of these galaxies, it is a big theory that there are black holes, and that's what would be found, supermassive black holes in the centers of a lot of these galaxies. And then we have spiral galaxies. This is what our own Milky Way galaxy is. They have two components, a flat disk area, which often contains a lot of interstellar matter arranged in a spiral-like pattern. And then in the centers they'll have a bar structure often, or a little bit of an elliptical bulge, consisting of old stellar populations without interstellar material, often associated with globular clusters. So with that, we see the spiral arms are often not quite as congested. The center areas are often where a lot of the older stars are, and of course in the centers that's where we feel a lot of supermassive black holes exist. Then we have irregular galaxies. There's no real symmetry or shape to them, and we kind of get them into two groups, where we look at galaxies simply having large amounts of dust that block most of the light from the stars. All of this dust makes it almost impossible to see distinctly exactly how many stars are in a galaxy. We have a picture here from the Hubble telescope, and pretty much every dot that we see here is actually a galaxy. There are really no singular stars in this picture. It is pretty much all galaxies, so every tiny little dot, wherever we look here, happens to be a galaxy. There are thousands of galaxies in this picture, and this is just one image from the Hubble telescope of this deep field where we can kind of look far, far, far into space and see this. And then we talk a little bit about some of the other material in our solar system. So up until this point we've talked about, and I have here this little pie chart showing us less than 5% of the matter in our universe is pretty much what we've spent the entire year talking about. Now we're going to look at the 26% here with dark matter. And dark matter, these are kind of some tough things to explain, some new ideas about what's going on in our universe. So in this theory here we have non-luminous material that exists in space that could take several forms, including weak interacting particles or highly energetic random particles that could have existed soon after the Big Bang. One of the reasons we do know, and they make up almost 27% of the universe, one of the reasons we do know that they do exist is that we can see the effects of them on light. So going back to relativity and how objects that have matter affect space and time and bend space and time, we can see that dark matter does affect light, and we call that gravitational lensing. And that's one way that we could actually detect dark matter, is by looking at how it affects the light from very, very distant galaxies. And actually when we're looking at galaxies colliding, we also have this dark matter that helps us kind of explain how it holds together galaxies. The gravity within galaxies isn't really strong enough to kind of keep galaxies together, especially at the way they're spinning. So dark matter kind of helps to understand how it pushes these galaxies into formation and keeps them from flying apart. And the other side of this is dark energy. And with dark energy, again, this is the huge, huge chunk of our universe. When we're looking at dark energy, it's a theory that this is a repulsive force that's counteracting gravity and that causes our universe to expand at an accelerating rate. When we looked at the Big Bang, we expected our universe to expand, and as we started to calculate how much it was expanding at, we actually seen that it was expanding at an accelerating rate. It's not slowing down in its expansion. So because we keep moving further apart, we can kind of witness the evidence of there's something out there called this dark energy, and it causes our universe to grow and expand even further and further and further. There's not a ton of other information out there on what exactly dark energy is. There are a lot of different theories. but it's kind of a new area. But that's all we have for this year's